it's lab weeks. For us, it's going to be lab weeks because we're in this hybrid remote model, but we are going to do several lab simulations on acids and bases to figure out molarity, mass, moles, mass percent of unknown acids and bases this week. Before we do that, though, I feel like we need to talk about your KSP of calcium hydroxide lab because that was your very first titration. So I just want to talk about a couple things I noticed, actually 10 things I noticed, and that will put you in better shape for the labs we will see during lab weeks. All right, we are going to go over the not so top 10 plays of the calcium hydroxide lab. Starting off with number 10. All right, when we are measuring, we have to make sure we have the correct number of digits. So yes, our burette counts backwards, but there are markings every 0.1 milliliter. So this is 10.1, 10.2, 10.3, 10.4, 10.5. And so that's exactly what I'm certain of is we are somewhere between 10.5 and 10.6. And so then I estimate one extra digit. I think we are, I don't know, maybe a little closer to the 0.6, so maybe 10.57 milliliters. So that 7 is estimated, but it is necessary. The thermometers we used in class only had markings every 1 milliliter, 1 degree Celsius. So you should have had 1 decimal point for your temperature markings. And then our graduated cylinders had markings every 1 milliliter. So you should have, and we use this for the measurement of the deionized water when you diluted the acid. So if we are certain of 21, 22, 23, so 23 point, and then you have 1 decimal place. So the graduated cylinders, which was measuring the amount of deionized water you added to the acid, that should have 1 decimal place. Your temperature should have 1 decimal place, and your burette should have 2 decimal places. I often have kids ask me, well, what would the markings have to look like if there were no decimal places? The only way we would have no decimal places is if I had markings every 10 milliliters. So 10, 20, I am certain of the tens place, and so I'm going to estimate the ones place. And so in this case, it would be like, 17 milliliters. So I'm estimating that 7. I know it's between 10 and 20, but I'm not sure exactly if it's at the 7, the 6, the 5, so that ones place is estimated. So not very precise because I'm estimating the ones place, and that would be markings every 10 milliliters. Number 9. So you guys got the acid, the HCl, it was 0.05 molar from a burette up front, and then you measured deionized water and added it to the acid before you did the titration. It was important that you knew the exact amount of water added and that you recorded to the proper number of sig figs in your data table. Number 8. The very first calculation wanted you to find the known concentration of HCl. Well, you were provided 0.050 molar HCl, but then, and then you took a certain amount from the flask, so final minus initial. So you measured how much was in the burette, you let go about 15 to 20 mils, recorded the exact amount, and then did subtraction. So I know the concentration of that certain amount of hydrochloric acid, and then what you did is you added water to it. So we didn't actually titrate 0.05 molar HCl. We had a lesser concentration because you diluted before you even started the titration. So your very first calculation was just a simple M1V1 equals M2V2, solving for that M2 because you diluted with water. Number 7. So ideally, you and your partner were able to get 2 good trials that were acceptable, and what was expected then was that you did all of the calculations for each trial and then averaged your final answers of KSP. The reason we can't average the amounts or the volumes or at any point in the process is because you could have had different amounts. So some of you even wrote in your error analysis like, oh, this wasn't good because I had a different amount of acid in my first trial than my second trial. maybe 15 versus 25. That doesn't matter. If you have more acid, it would just take more volume of the base to titrate. But we can't be averaging the volumes because you had different amounts. So all we could do was each calculation once per trial, and then once you had your KSP value as your answer, then we would average the final answers for the KSPs. Number 6. Okay, so the color change in this titration was telling us that all of the H plus in the flask was converted to water by the hydroxide from the calcium hydroxide. So if you think about what we know now, HCl is a strong acid, CaOH2 is a strong base. If I break this apart and just care about the things I care about for strong acid, strong base, I'm going to skip the full ion equation. I get 2H plus, there are 2 OH minuses because of this 2, makes 2 H2Os, which we can always simplify. H plus OH minus makes water. Here's the important part. The moles of H plus when your solution turned pink is equal to the moles of the OH minus when it turned pink. Yes, we had a 2-to-1 stoich in the overall equation, so if you did not do the net ionic, that is okay. You did not know about strong acids and strong bases breaking apart. But 2H plus is here, right? 2 of the HCl, 1 of the calcium hydroxide, but then what we found was that there are 2 hydroxides for 1 calcium hydroxide. So we could have either used this 2-to-1 relationship and then taken into account the 2 here, or we could do the net ionic equation and it's 1-to-1-to-1 and gotten the same exact answer. Number 5. So if we do a BCA table and we figured out the moles of OH minus because it was a 2-to-1 from the acid to the base, and then there were 2 OHs in 1 mole of the base, right? 2 hydroxides in 1 molecule. How do I find the molarity? Well, to go from moles of OH minus to molarity, we are going to divide it by the volume of the calcium hydroxide used. How do I figure that out? Well, you had calcium hydroxide in your burette for the titration. You recorded how much was starting, close to that very top probably, and then you recorded the final volume when you stopped because it turned pink. So if we subtract those and get the difference, we can figure out the volume. So if I take the moles divided by the volume, and be careful, make sure that volume is in liters, not milliliters. That is how we found the concentration of OH minus in the perfectly saturated solution. Number 4. All right, number 4 has to do with our air analysis. You had to explain some potential sources of air. So anytime there is human error, calculation error, rounding error, those are not going to be real things we want to talk about. For example, if you made a human error, you spilled, you measured something wrong, you did a calculation error. Some of you said, well, I probably calculated it wrong. Here's the thing. If you know that you made a mistake in the lab, or you know you made a calculation mistake, you should fix them before you submit your lab. Or if you spill, you should run another trial, right? I know some of you let your burette get down too low and now it was past where all the markings were, right? That's a human error. You need to redo that trial because you don't have an accurate measurement. Okay, rounding error is not going to be a factor if you measure with the correct number of significant digits and use sig figs correctly in your calculations. The other thing that a lot of us talked about was because we did 2 trials, you mentioned that you used different amounts of the HCl. That is fine. If you use more acid, because remember the point of it turning pink is that that's when moles of the acid equals moles of the base. So if you had more acid to start with in your flask, it would have just taken more base. And then you add more volume, right? So we were able then to, you should have been able to get the same result because you're dividing by a larger volume that time. So having different amounts shouldn't have made a difference because we are doing separate calculations and averaging. Number 3. So what should we put in our CER? Well, I want to talk about the evidence. The evidence needs to be specific data or numbers. So don't just tell me, I calculated this. Give me the actual number. I'm looking for a number with a unit. And those are the most important numbers that helped you get your claim. In this case, the KSP, your average KSP, was your claim. So what were the most important numbers to get there? Well, KSP was equal to calcium 2 plus times OH minus squared. So the molarity of calcium 2 plus and the molarity of OH minus, I was looking for those numbers as your evidence. Some of us did not include numbers at all in our evidence, and some of us try to include every single number. I measured this much acid, and I added this much water to it, and I added 1 drop of phenol. No, don't tell me every number. Just tell me the most important numbers. And then in your reasoning, that's where you explain your process and why your process helped you get this. In this case, for our reasoning, I would talk about how in the burette we had a perfectly at equilibrium calcium hydroxide solution. So we used a titration with a known molarity of hydrochloric acid because we knew when it turned pink that moles of acid would equal moles of hydroxide. And if I can figure out the exact amount of hydroxide dissolved at equilibrium, I could also, using a stoic ratio, figure out the exact amount of calcium dissolved in that solution at equilibrium, which allowed me then to solve for KSP. Number 2. Okay, anything that you're going to measure in lab, temperature, volume, right? Initial recording, final recording, those need to go in your data table. And your data table needs to be in your lab notebook before the lab ready to go, because this proves that you actually know what you're doing in the lab and you know exactly what numbers you're going to be measuring and what numbers you need to be successful on your calculations. So you should know everything you're going to measure ahead of time, because anything you need in your calculations needs to be measured, and you need to understand those before you show up to lab. And the number 1 not so top 10 play of the KSP lab is we have to come to lab prepared. So I had some kids show up without their lab notebooks ready to go. That's one situation. I had some kids that showed up with their lab notebooks totally done, but they just kind of copied down the procedure or drew pictures without really understanding and visualizing what they needed to do. So you need to come to lab prepared. You need to email questions ahead of time or come in for help if you don't understand some of the directions. That's going to be a huge thing in college. In college, if you show up to a lab without your pre-lab done, you are kicked out and it's an automatic 0. If you show up with your pre-lab half done or it's done but you don't understand what you're doing and you make too many mistakes, you are going to waste time and not be able to finish your lab in the allotted time slot, and they will not allow you to come back after your time slot. So you have to be prepared, and if you don't understand something, you need to speak up prior to coming to class. And then I just wanted to pay tribute to some of our very first titration efforts. I got some, as Mr. Charvella calls it, some unicorn pee in some of these guys. We kind of overshot maybe our equivalence point a little too pink for what we like. But don't worry, after our first trial, some of our groups got there a little bit better here. So we were making some progress. And then these ones I would like to just kind of put in the Hall of Fame for our very first titration. This is pretty good for our first effort at a titration. Look at that nice baby's butt pink. Love it. That's our goal every single time, guys.